Hello everyone. In this section, we trying to do the so this is the review of third part of review. So this is review antiderivatives. Antiderivatives. So so in the Thomas book, it is section 2.8, 4.8, section 4.8, and in the Stewart book it is section 4.9. Okay, so so if you need further detail, you can check those sections. Okay, so so let's start with the definitions. So so the definition. So antiderivative. Okay, so we say a function f, we normally use uppercase letters for that. A function f is an antiderivative of f, of small f, on an interval I if the derivative of f, big F, is equal to the small fx for all x in the interval I. So that's the kind of idea, So we say a function is a antiderivative. Once you take the derivative of that function, you get the function back. Okay, small function. And then we have what we call the most general. So so if f is an antiderivative, if f is an antiderivative of f, then the most general antiderivative of f is, so if you know uppercase F is the antiderivative of f, then the most general antiderivative you can write as fx plus c. Okay, fx plus c, where c is an arbitrary constant. Okay, so that's the idea, arbitrary constant. C can be anything. So in notation, we can write this most general antiderivative using the integral notation. Okay, using the integral notation. So so that means the integral of fx dx we write as fx plus c. So that's any antiderivative. So that's how we write it, and this is what we normally call the definite integral. Indefinite integral, because indefinite means there are no numbers, so we call this is the indefinite integral. Indefinite integral. Okay, So that is simply if. So that's a notation. So we call this the indefinite integral. So I'm going to give you like a simple problem here just to kind of get the idea. So this is a very simple idea. So for example, we know that the derivative of x squared is 2x, right? Derivative of x squared is 2x. So that means the antiderivative of 2x is, so the antiderivative of 2x is x squared. But if you need the most general one, we can add a c here. So when you write the notation, we write the most general one. So it's like a, so just go backward. Okay, just go backward. So this is the kind of idea we try to understand. So as you can see, that's very simple. So that means if you are good in derivatives, you are automatically good in integrals. Okay, because you just need to think backward. So let's look at several examples. So how about these? So let's say find the antiderivative. Or we're going to say most general. Most general means you add a c. Okay, so let's see. So as we did before, 2x. So you want to think of a function. Once you take the derivative, you get 2x. So what is that function? It is x squared. Okay, so since we need the most general, we can add a c there. How about cosine x? How about cosine x? So you can see if you go back, so we can add these two things always. So what are the two things? We can add the integral sign, and you have a function and the dx. Okay, so like that. But it can be like even any other variable, like you can say dt. So it doesn't matter. This is just called a dummy variable. Dummy variable. So it can pretty much be anything. So it doesn't matter. Okay, so you just use that. Okay, so that's the notational thing. So okay, cosine x. How you get the cosine? What is so what function has the derivative as cosine x? What function has the derivative as cosine x? That is simply sine x. Okay, so it's sine x. So sine x plus c. How about this one? Let's say 1 over x plus 2e2x. Okay, when you have more functions, we put a parenthesis around just to make it clear. Okay, so if you have two functions, let's do one by one. What derivative, what function has the derivative 1 over x? What function has the derivative 1 over x? Maybe you can remember that is a natural log. So it's a natural log, but don't forget the absolute sign. Okay, it's very important. Ln x. How about the next one? You can see e to the 2x. If you have e to the 2x, you know that when you take the derivative of e to the 2x, when you take the derivative of e to the 2x, what do you get? You get 2e to the 2x. Okay, so that means this is a complete derivative of a function. It's a complete derivative function. What function? E to the 2x. Okay, so that means it is e to the 2x, because we know that if you take the derivative, you get 2e to the 2x. You can say since the derivative of ln x plus e to the 2x equal, ln x going to give you 1 over x, and then this one going to give you 2e 2x. Okay, so that's the reason. So you just think backward. Let's do a few more. How about let's do a function like this. So number 4, we can say sine 2x dx. Okay, so we know there's a sine, that means it is a negative cosine. Okay, so it's a negative cosine 2x, and you know that the inside function does not change. But if you take the derivative, of cosine 2x, you get 2 sine 2x, negative 2 sine 2x. That means you get a 2. So to cancel that 2, you have to put a 1/2 there, so that you're going to cancel each other. Okay, now you can see, if you take the derivative of negative 1/2 cosine 2x, you get sine 2x. Okay, and again plus c. Again, since the derivative of negative 1/2 cosine 2x equal what? Negative 1/2, and then take the derivative. Once take the derivative, you're going to get a negative 2 sine 2x. Okay, and then you can see this get cancelled, negative cancel, 1/2 get cancelled, you get sine 2x. Okay, so that's the idea. So you think backward, and then how about something like this? So number 5, so let's say antiderivative of 1 over square root x dx. How about that? So you can see because when you take the derivative, you have to subtract 1, right? Or subtract 1. So when you subtract 1, so you can see this is something like this, x to the negative 1. Okay, so that means when you subtract 1, you get this. That means when you talk about the antiderivative, you want to add 1. So that means it's going to be x to the 1/2. But what will happen? Once you take the derivative, you know that you get 1/2 in front. So to cancel that 1/2, you have to divide by 1/2 plus c. So if you simplify this, it is 2 square root x plus c. So that's the kind of idea. Now what we can do is we can have a list of functions here, but this is not a complete list, but I'm going to give you a list in Canvas. Okay, so let's give like a few common antiderivatives. So let's say table of antiderivatives. So what are they? So I'm going to go with xn. So what is that? It is n plus 1 x to the n plus 1. This is when n not equal to negative 1. If n equal to negative 1, what will happen? So if n equal to negative 1, that means 1 of x. That's the n equal to negative 1 case, you're going to get ln absolute value x. Okay. So this is not the most general one. This is just the just one you had a c there. Okay. So number 2. Number 3, we can go sine kx. So what will happen sine kx? You know that when you take the derivative, k comes out, so to cancel that you have to put 1 over k, and also there's a negative sign, so negative 1 over k cosine kx. And the number 4, cosine kx, that is 1 over k sine kx. Okay. And then we have we can go with secant. I'm just giving you like a few common ones, but you can see the larger list in the table. So secant squared. What is secant squared? 1 over k tan kx, and then secant tan. So secant kx tan kx, which is what is secant tan? Where you get the secant tan? When you take the derivative of secant, right? So it's a 1 over k secant kx. Again, this is not the full list. This is like some common ones. And then we also have 7 e to the kx. E to the kx is 1 over k e to the kx. How about a to the kx? Not e but a. So what happened here? So it's going to be a to the kx, and then k comes out, ln a comes out. And then 9, we have some trigonometric functions. For example, 1 over a squared minus x squared square root. So that is sine inverse x over a. And then we have number 10, 1 over a squared plus x squared. 1 over a squared plus x squared. So it's a 1 over a tan inverse x over a. So those are several common ones. Yeah, so I can give you maybe 2 more. 11 cosecant squared kx, which is negative 1 over k cotangent kx. And then number 12 cosecant kx cotangent kx, which is negative 1 over k cosecant kx. Okay, good. So those are the kind of major list, but I'm going to give you like a larger list in Canvas, which has 22 integrals. Make sure that you kind of go over that and remember them. We can definitely help you, but some of them you can prove, but these things like just coming from Calc 1. Okay, so yeah, so this is the kind of common list. Also, I'm going to give you one more. This I'm going to call it 9 star. So when you have a negative sign in front, you can call it the negative of this, or you can also say cosine inverse x over when you have a negative sign, but that's optional. So the same thing works with that one. If you put a negative sign here, so it is a negative 1 over a squared plus x squared. This become cotangent, so 1 over a cotangent x over a. So you can do that. Okay, good. So I mean, just for the moment we can use this list to do like few more examples. So let's see what we can do with this. So here the most important one. So these are the most important one. I'm gonna put a kind of box. So this is one of the most important one, and this is one of the most important one, and this is one of the most important one. And this is one of the most important one. Okay, those are most important ones. Very, very common, is everywhere pretty much. Other things are also important, but remember these because these are like pretty much everywhere. Okay, so let's try to do like some examples from this, and just to kind of understand a little bit more. So so what we have, so we had 5, so let's do a few more. Number 6. So number 6, integral of cosine x over 2 dx. Now you can see the k is 1/2. So what it says is a 1 over k. It's a cosine, that means a sine kx, so it's x over 2 plus c. And you can see division means divide by 1/2 means multiply by 2, so it's a 2 sine x over 2 plus c. So we have that. And how about this, e to the negative 3x? So according to the formula, it says 1 over k e to the kx plus c. You can write this one as negative in front, 1/3 e to the negative 3x. That's how we normally write it. That's the best way to write it. Number 8. What else? Yeah. Now we can actually do this problem in a different way. Remember the problem that we had is square root 1 over square root x dx. So we can do this one as x to the negative 1/2. So that means the theorem says you add 1, that means 1/2 divided by that 1 plus c. So in other words, 2x square root plus c. So you can do that. Okay. One more. How about 2 to the x dx? So if you have 2 to the x, so what's going to happen? So it is 2 to the x divided by ln 2 in this case, ln a plus c. Okay. So and then number 10. So let's do a little complicated one. How about we have 2 here, 3 square root x plus sine 2x dx. So and how we can do it? You know that this, you can take this number out. You can rewrite this one as x to the negative 1/2 as before, dx plus sine 2, you split them as 2, then you do 1 by 1, and here you get 3, and you add 1 divided by that, plus here sine k equal 2, so it's a 1 over 2. Sine means cosine 2x, and with the negative sign, so with the negative sign plus c. So if you simplify this a little bit, so you're gonna get 6 square root x minus 1/2 cosine 2x plus c. Okay, it's not that bad. Let's do maybe one last problem. So how about this, number 11? A little bit more. So we can say x squared minus 2x plus 5 divided by x squared. How about that? And you know that in integral calculus there is no quotient rule. So what do you do? You can probably simplify this before. So if you simplify, if you divide by x squared, you get 1 minus, if you divide by x squared, you're going to get 2 over x, and then you're going to get 5 over x squared. So first divide, and then you can write them as powers. So the first one is 1, next one we already know, second one you can write as 5x to the negative 2. Now you can do 1 by 1. So from the first one you get x, from the second one it is 2 over x, so 2 is a constant, and then you have 1 over x. 1 over x means natural log, so it's a natural log x. And the next one you can also use a power rule. So what's the power rule? You can add 1, so that means a negative 1, so divide by negative, so x to the negative 1 means 1 over x, so that means a negative 5 over x plus c. Okay, so these are the problem for antiderivatives. So what you want to do is when you do the homework, so what you can do is look at the table and think backward. Okay, when you think backward, you can get the answers quickly. So maybe let's just do like a few more examples. How about this number 12? So I would like to do this one, square root x plus 1 over square root x. Again, so this is x to the 1/2 plus x to the negative 1/2. And then if you do 1 by 1, you can add 1, so it's become 3/2 divided by 3/2 plus you add 1, so x to the 1/2 divided by 1/2 plus c, and then divide means multiply upside down, and x 3/2 divide means multiply, and so yeah, so it's clear. Alright, so you want to simplify all the way down like that. So 13, what's a good one? So yeah, how about this one? Integral of sine pi x minus 3 sine 3x. Yeah, again do term by term. Here the k equal pi, this is sine. Sine means negative cosine. This is a negative 1 over pi cosine pi x, and again this is sine, so negative with this negative become positive, so 3, but as a k equal 3, so divide by 3, cosine 3x plus c, and then you simplify if you can. So here you can simplify this a little bit, cosine pi x, this is get cancelled, so you get cosine 3x plus c. How about this one? For secant 3x tan 3x dx. How about this? For secant 3x tan 3x dx. Can you recall anything? You can probably go back and look at the table what we have. Do you see anything in the table? Yeah, you can see number 6. Secant kx tan kx is 1 over k secant kx, because the derivative of secant is secant tan. So since the derivative of secant is secant tan, if you get the integral, you're going to get backward. So that means it's a secant tan situation. So it is 4 is just a number. Here the k equal 3, so 1 over k. This is secant 3x plus c. I mean, that's it. 15. How about this one? 1 over 2 x squared plus 3 dx. Will that match with any of those formulas there? Again, let's go backward. you can see that number 10 we have 1 over a squared plus x squared. If you see 1 over a squared plus x squared, it is 1 over a tan inverse x over a. So we can use that formula now. So that means, what is a here? Because you can write 3 as square root 3 squared. So a equal square root 3. The 2 is just a constant. So that means 1 over a, that means 1 over this with 2, 1 over 2 square root 3, 2 is from there, and tan inverse x over a means square root 3, okay, plus c. Okay, so this should be enough, and you can see that it's not that difficult. You can just think backward and get the answers. Okay, so yeah, so I'm going to stop stop this right now for the antiderivatives formulas, and you can start working on the homework. Okay, so end of antiderivatives. Okay, so thank you.